Hi, in today's video, I'm going to teach you how to perform hypothesis testing on one population mean using a different test. We call it the T-test. And as you might have learned before, we perform hypothesis testing using the Z-test if the population standard deviation is known, and this is regardless of the sample size. As long as the population standard deviation is known, which is our sigma, then we have to perform the z-test. Now there are cases in which the population standard deviation is unknown, but if the sample size is large enough, that means n is greater than or equal to 30, the appropriate test is still a z-test. So now we'll look at a case, and that is, suppose that the population standard deviation is unknown but the sample size is no longer large, meaning to say that the n is less than 30. If that is the case, then we have to use what we call a t-test. Whenever we perform hypothesis testing, know that the process will be the same for all topics, and the only thing that will change from one topic to another is the test statistic that you have to use. Now, in the case of the population standard deviation is unknown and the sample size is small, we will be using the t-test that will use this test statistic t formula x bar, which is the sample mean, minus the mu sub 0, the hypothesized mean, which will be identified in the null and alternative hypothesis, and S is the sample standard deviation. So as you can see, you cannot use sigma because sigma is unknown as stated in the condition. So that sigma will be divided by the square root of the sample size n. Now, unlike the z-test, there is this what we call the degree of freedom that we have to follow when we apply the t-test. And that degree of freedom will depend on the sample size n. Now, the formula for the degree of freedom is basically 1 less than the sample size. So if you have a sample size of 15, then the degree of freedom when you apply the t-test is 15 minus 1, or 14. This degree of freedom will be used later on when we identify the critical values for the t. So there is no better way to understand this than to look at an example on how it is applied. Let us consider the following. Ramona heard that the average grade in mathematics of her class is at least 88. She was not convinced by this, and so she decided to use hypothesis testing to check if this claim was true. She got a random sample of 10 classmates who gave their grades in mathematics as follows. Now let us assume that the distribution of the grades is normal. Based on the sample data, what would Ramona's conclusion be on the average grade in mathematics of her class? Use 5% level of significance. Now, before we even start performing the hypothesis testing, we have to check first if this will fall under the t-test. Keep in mind that the condition must be the population standard deviation is unknown and that the sample size is less than 30. Now, there is nowhere in the problem that states about the population standard deviation. So we know that the population standard deviation is unknown. At the same time, if you look at the sample that we only have a sample of 10 students, so that 10 is less than 30, which means the sample size is small. And with that, so this will be under the t-test. Now you might have noticed a statement that states, assume that the distribution of the grades is normal. Now this statement is telling us that the population distribution is normal And this is also needed to allow us to perform the t-test. So let us begin with the hypothesis testing. First, we need to assign mu as the true average grade of the students in the class. The true average grade is the population mean, or the population mean score of the students, or mean grade of the students. So with that, we will be writing our null and alternative hypothesis. Our HO must be, so if we refer to the statement, Ramona heard that the average grade in mathematics of her class is at least 88. When we say at least 88, that is greater than or equal to 88. And as we all know, this statement will fall under the null hypothesis because it is containing the equality. So we have mu must be greater than or equal to 88. Now with this, our alternative hypothesis H1 will be mu less than 88. So this will challenge the null hypothesis mu greater than or equal to 88. And then after that, we proceed with identifying the significance level. In the problem, it says the significance level alpha is 5%. So alpha is 5% or 0.05. The test that we are going to use here, as we already know, is a t-test. And the formula is t is equal to x bar minus mu sub 0 over s over the square root of n. Now because the alternative hypothesis is mu less than 88, we will be expecting our diagram to be something like this. And then the area of rejection is on the left. Now just one observation that I want you to have is that the graph for the t-distribution looks like the graph for the standard normal curve. So how are t-distributions different to the standard normal distributions? The difference is on the height of the graph. The yellow graph is a standard normal distribution. T-distributions are flatter than the standard normal distribution, and the smaller the sample size we use, the flatter the graph will be. So it will go lower and then lower. But if we will increase the sample size, then the curve will go higher. And if we continue to increase and make the sample size large enough, it will be approximating the normal curve. So with that, the boundary of the critical region is no longer a z of alpha, but it's a t of alpha, which is associated by a degree of freedom n minus 1. If the critical region is on the left side, the t of alpha will take a negative number, but if the critical region is on the right side, then the t of alpha is a positive number. Now here on the right, we can see an example of a t-table. Now unlike the z-table versions that you will see online, a t-table will only list all the positive values for the t. So how are we going to use these numbers? Now, the first thing that you need to note when you use this exact version of the t-table is to focus on that one tail. Now these numbers that you will see here, that you can see from the table, will be the subscript of the t that we are going to use. So if my alpha is 0.25 and the critical area or the critical region is concentrated on one side, then the 0.25 will be my subscript for the t. So in our example, since the alpha is 5% or 0.05 and the alpha is concentrated on one side, then our t of alpha is negative t of 0.05. So the first thing that you need to do is to locate this 0.05 as the subscript on the one-tail row. And the 0.05 is located here. Now there are so many numbers on the column of 0.05, and you have all these numbers to choose from. This is where the degree of freedom will come into play. Since Ramona only sampled 10 students, then the sample size is 10, and the degree of freedom, which is n minus 1, should be 10 minus 1, which is equal to 9. So under the 0.05 alpha, we have to go to the df, the degree of freedom 9. And then we trace from the table what will be the number that will be the intersection of the two values. So we have 1.833 on the row of 9 and on the column 0.05. So we place that 1.833 on the critical region's boundary. So this is 1.833, but since it's on the left side, then this must be a negative number because the center is at 0. So with this, the decision rule must be either of the two. We will be rejecting the HO if the T, the one that we will be calculating from the T formula, if that number is less than negative T of alpha or less than negative 1.833. That means the number will fall under the critical region. So that means we have to reject HO. Otherwise, if the number is higher than the critical value, negative 1.833, then the corresponding decision must be do not reject HO. Then we go now to the computation of the T. So that is our step number 3. So again, T is equal to x bar minus, we have mu sub 0 over s over the square root of n. To calculate this, we need to know the following. We should know what is the x bar, the sample mean. We should know the s, the sample standard deviation, the mu sub 0, and the sample size n. Now the mu sub 0 is the hypothesized value. The hypothesized value is the value we use in the null and alternative hypothesis. That means the mu sub 0 is 88. So we have 88 and the sample size is equal to n. Now for the x bar and the sample standard deviation, we have to make use of our data, and that is, or these are the numbers that are the scores of the students we sampled. So we have these 10 numbers here. The sample mean is basically the average of these numbers, and then the sample standard deviation is the standard deviation that you will get from these numbers. Now, the easiest way to find the sample mean and the standard deviation of these numbers is by using your calculator. So get your calculator and compute for the sample mean and the standard deviation of these numbers. In this video, I'm going to assume that you know how to find the sample mean and the standard deviation of these numbers using your calculator. If you don't know how to find these values, there are several videos that you can refer to online and follow the instructions on how to find the sample mean and the standard deviation. Based on my computation, the sample mean is 85.9 and the standard deviation is 6.2973. So I'm using up to 4 decimal places whenever it is possible. So with these numbers, we just supply the formula with x bar 85.9 minus mu sub 0 88 over the quantity sample standard deviation 6.2973 divided by the square root of n, which is equal to, so this must be 10. So based on my calculation, this value is equal to negative 1.0545. So I rounded off the number up to 4 decimal places. So now we go to step number 4, and we immediately compare this number to the critical value. So as with our diagram, the critical region is on the left with the critical value of negative 1.833. So using that number, we have to locate that on the diagram, and we should be able to see that that number is on the right side of negative 1.833. So if the 0 is at the center, we know that it should be a number, or that number is closer to 0 than the negative 1.833. That simply means the number is lying outside the critical region. So which makes the decision to be, so if the number is outside the critical region, the decision is do not reject HO. So this means that the null hypothesis, which is mean is at least 88, should not be rejected. So with this, we can say that the true average score, or the average grade rather, so of the class in math is at least 88. In other words, there is no sufficient evidence supporting the alternative hypothesis that the average score is less than 88. So this is the standard way of stating our conclusion. And we know that this is, or these findings, is based on the 5% significance level. Okay, so that's how we perform hypothesis testing using the T-test. So just to summarize, again, the process is basically the same with all the hypothesis testing. The only difference is when it comes to the type of test, you have to identify what type of test statistic formula you are going to use. In this case, we use the T-test formula because the condition is under the T-test. Also, you have learned how to read a specific table, we call it the T-table, which will be used in relation to our critical value. So once we have computed the T statistic, we will be comparing that to the critical value in the diagram, and that will lead us to our decision and conclusion whether to reject or do not reject the HO. Okay, so that's all for this video. I hope you know now how to perform hypothesis testing using the T-test.